Thank you very much, Leisha, and thank you, Magda, for organising and being flexible with the dates and everything for this. Great. So I'm delighted to be here and to see so many faces, especially my mum is here, and my husband, and my two daughters. They're here, with some cousins as well. So and of course, all of you guys as well. Yeah, it's great. I look forward to chatting to you afterwards. So let me just figure out. So the title of my talk is The Magic of Magnetics and Power Electronics, from wireless charging to enabling cancer treatment. So I know magic might have been a controversial word, but hopefully I can show you some of the magic that I think we're doing anyway. Okay, so just to say who I am, first of all, well, I'm Maeve Duffy. I'm the fourth of 8 children. I did my national schooling in Carrick-on-Shannon. My dad was in the Guards and he got promoted, and that meant he had to move. Thankfully, I didn't have to move to get promoted. So he moved to the border, and eventually we all moved up there too, and they settled in Bundoran, which is a beautiful part of the world. So yeah. So my career to date, I did my bachelor's. I've been around a long time, so I'm delighted to be at this point. I did my bachelor's here in 1992, and I was delighted to be able to stay and do a PhD with Professor Ger Hurley, who's here, in 1997, after which I spent 4 years in the Tyndall National Institute in Cork as doing postdoctoral research. I was very lucky to get a job back here in 2001. It took me a good bit of time to get promoted after that in 2022, but there's been a lot of improvements in that promotion process at the university level, and I'm delighted, obviously, to be at the stage I'm in now. So maybe, first of all, to explain a little bit to you about what magnetics and power electronics is about. I'll try and keep it as simple as I can. So you can see this is a charger for an Apple MacBook. It's quite an old one, I think. And somebody has done a teardown of that. So there's lots of people out there who pull these things apart to see what's inside, which is great from an engineering point of view. So what a charger is, you probably know. You plug it in, and what it does, it converts the electricity that's provided from the mains into a form that will charge your battery. So it goes from AC into DC. And what you'll see inside in it is there's lots and lots of these components that have wires wrapped around them. And this one also has wires inside, and this one, and I don't know where else. Anyway, at least half of the volume of the power supply is made up of magnetic components. So the size of it, the cost of it, the weight of it, and its performance is very much determined by the performance of those components. And it's the same if you open up a mobile phone. It's the same thing. There's lots of little circuits inside, because in your mobile phone you've got a screen that needs one voltage level. You've got a speaker that needs another voltage level. So once you feed up your battery, or you fill up your battery, then the battery has to be converted into all these other voltages using similar type circuits, smaller circuits obviously, and that's where it's going. That's where the demand for smaller magnetic components and lighter power electronics. So this would be a power electronic circuit, and those components inside would be the magnetic components. So as with everything, everybody wants things to be smaller and lighter. Like the phones, the original phones, you know what they looked like. They were bricks. Now we have, mine is not the smallest or the neatest, but all of that is demanding that everything, all the power equipment gets smaller and smaller. On the other hand, the mobile phone that you would have got 10 years ago would have been a very basic device in terms of what it could do. Whereas now, you can make a phone call, you can ring somebody the other side of the world. You could probably ring someone on the International Space Station. I didn't check that, but I'm sure you can. Well, you can play music from the International Space Station and relay it down to Earth. So your mobile phone is a lot more powerful than it used to be. Effectively, it's a very high-performing computer. And if you look at this graph, just look at the yellow line. This is the amount of power that the computer chips inside a mobile phone or a PC or anything that's processing information, you can see it's increasing. That's up to 2020. I didn't find any predictions for the power that is going to be needed for the next 10 years. But I know that with AI, obviously your computer is going to be working much, much harder now. And it can only do that if it has more power. So the combined issues of trying to make things smaller and then fit more power into those smaller components, that can only be achieved if we have advancements in the power electronics, the circuits that process the energy, and particularly in the magnetic components. So that's where I've been mostly focused, and I'll try and go through it in a coherent way so that you can understand it. So starting with my PhD in 1992, it might look like quite a simple thing at the moment, but my PhD focused on predicting the electrical performance of these small devices. Well, some of these small devices. They're called spiral inductors, and they perform one important function, like those big magnetic components you saw. It's one of those, but on a smaller scale. So I developed models to predict the inductance and the losses of those devices based on the structure of them. So you can see this is a photo plot of a screen printing process to produce spiral inductors using screen printing. And these turns would all be one on top of the other. This is like a cross section through half of it here. So you can see it's 4 layers. So the current would come in here, come out there, go around here, and out here, and so on, all the way down. So that would make up an inductor, and I put the maths behind it. I thought it was done before. It hadn't been, so I was delighted that there was enough work in it to keep me busy at maths and applied maths for magnetic devices. Why it was important was the alternative to those type of devices were these wire-wound components. So they functioned in the same way, but the problem with those is as things were getting smaller, the height of the device was being restricted by those, and also they weren't that reliable. If they got pushed out of shape, then their electrical characteristics would have changed. So with these devices, they're flat and they won't move, they won't change over time, except if they get old and they decay. But of course, the processes would be developed to prevent that from happening. So to enhance the properties of the coils, we added some magnetic material so that they could perform at a higher level and do the same function but reduce the losses, so to make a more efficient component that could be used then in a power conversion circuit and make the circuit more efficient. So that's an example picture of some of the types of devices that were being made. So you have a magnetic plate on the top, on the bottom and on the top. And alongside, my developments in predicting how these things could work, there's a whole host of researchers developing processes to allow people to make them using different technologies, including the team at Tyndall, which I, through Professor Hurley, got to know and got to work with even during my PhD. So that work was published there was 2 papers that, 2 IEEE transactions papers that I wrote as part of my PhD, and they attracted, surprisingly, quite a lot of citations, and they still continue to attract citations. So people reference the equations that I developed in my PhD, and I was very interested to know, where the applications are, and they're very wide-ranging. I'm just going to show some of the most interesting ones that you can probably relate to. The first one is wireless charging. So I'm sure some of you, well, not everyone, would have a phone. Some people have phones, so Apple phones can be charged wirelessly by putting them on a charger platform like this. So a lot of research in developing wireless charging systems would have referenced the equations that I was producing, because wireless charging consists of a coil in this platform and then another coil in your mobile phone or your device that you're trying to charge. And when you apply a voltage to this coil or get current flowing in this coil, you can induce a voltage in this one wirelessly. So I guess that's one of the first magic aspects. So you can induce a voltage in the coil without having to plug it in, just put it sitting on top and even move it away from the coil a bit, and you'll get your phone to charge. The work was cited quite a lot in relation to that. And one person in particular, Professor Ron Huey, he's from the University of Hong Kong, he was developing standards for wireless charging, and he had a whole load of patents and so on. And he would have widely cited our work, and he would have always credited us with supporting the development of that standard and his products. Just to show you again, this is just showing you the coils inside. That's not the same device. This is a small scale demonstrator of a wireless charging system for electric vehicles. And it's just showing how that, you know, it'll even transmit power when the coils are at a distance and also when they're not fully aligned with one another. So it's a very exciting area of research. And, you know, it's wireless charging for phones, electric cars, medical implants, and so on. The other interesting application is domestic, induction cooking. Domestic induction cooking and any induction cooking. So how that works is it's similar. You've got a coil that's inside in your cooker that's plugged in, and then you put your cooking pot on top, and what happens is it's the same principle. This is effectively acting like a coil because it's a conductive material, and what it does is you get power transferred from here to here. And I should say Professor Ger Hurley, I think, completed his PhD, or sorry, his master's in MIT on that topic. He built the circuits for driving these coils, so I was well supervised when I was doing my design of the coils and modeling of the coils and so on. Anyways, normally when we're designing coils and induction systems, we want to reduce the amount of heat that's in it, because we want to reduce the losses and make it as efficient as possible. When we're doing cooking, of course, we want to maximize the amount of heat that's transmitted to the pot. So that's kind of the opposite way of looking at magnetic design for wireless coils. But equally, the equations that we developed were able to model the same situation. And there's a very famous research group in Oviedo who are working with a lot of commercial companies that are producing induction heating systems. And we've been cited by those. So we were delighted to be able to say that our work was recognized by them as well. And there's lots of other applications. I just thought those two you could probably relate to. So then after my PhD, because I had been doing some work with the Tyndall National Institute on short-term projects, I moved there to Cork. It was great. It was like moving away down south with the weather and whatnot. And the distance, of course, from Donegal, it was a long way, so it did. We used to have to book holidays to go home or whatnot. But anyways, the difference between my work in Galway was very theoretical. Of course, we did work with them, and I had some appreciation of the limitations of manufacturing and so on. But in the Tyndall Institute, they've got lots and lots of access to facilities for producing things using different manufacturing technologies. So the first project I worked on was designing spiral coils on printed circuit boards. And I don't know if you know printed circuit boards, but they're usually multi-layer boards, and inside you've got different layers of copper that you can put coils like this on. So we worked on a project where we were focusing on the magnetic components on the internal layers of a printed circuit board. And then there was other partners in a European project working on integrated capacitors and other passive components. so that there would be enough space then on top to fit the more complex integrated circuits that offer the intelligence, if you like, into the circuit. So it's like a multi-story building, if you like, and trying to fit more into the same footprint. We also looked, so there was, in the team in Tyndall, there was people focused on developing magnetic materials and processes for putting magnetic materials onto printed circuit boards. So again, that gave me more scope to develop models for predicting how would those magnetic materials enhance the performance of the coils that are inside. So you can see the coils are in here, and we've got magnetic material on top and bottom, and then there's through holes here, and they're also magnetic, they're electroplated, so it produces a core around the windings, much in the same way as traditional inductors would be produced, except now they're being produced on printed circuit board. And that's a picture of one of the real devices. And what was exciting about that is that we patented that because the shape of the slits in the core, again, the idea there is to reduce the losses to make it a more efficient device. We were also looking at magnetic coils or spiral coils on silicon. Again, they have prototyping facilities and silicon laboratories that they're able to make, prototypes that you wouldn't normally get in industry, small scale, and they were able to experiment with processes and so on. So there was a different type of spiral coil here. It had much higher height and much narrower tracking. And again, that's to try and to reduce the losses in the inductor as much as possible. And again, they were putting a magnetic core around the windings now, but these are tiny. That's, that's about 1 millimeter. That distance is less, 0.75 of a millimeter. So very, very small. So this technology was being spearheaded by Professor Kino Mahuna, who's in Tyndall. He's leading a research group on micromagnetics and power supply on chip in the Tyndall National Institute. And his vision was to develop the technology enough that we could make the magnetics disappear into ICs, ICs being integrated circuits. So I'm borrowing that bit of magic from Keen. So he coined that phrase, but he's actually very famous in the semiconductor world for doing this power supply on chip. And just after I left, the team at Tyndall, like I said, there was people developing materials, processes. I was developing models. There was other people working on testing and so on. That team, under Keen's guidance, we had 2 multinational companies license the technology, the know-how for the technology, all the know-how, so not just any one bit. I'm actually not sure how much of the know-how I contributed to, but I know that I was told I was part of the thing. So they licensed that technology a long time ago, and about 2 to 3 years ago, I got a text from Keen really excited to say that the technology had been implemented in products by one of those very famous multinational manufacturers. So he was over the moon, and I mean, I contributed in some way to that, and I was delighted to. But as I said, the team in Tyndall is famous for that, and I was privileged to be part of that. So then I came back to Galway. I got a lecturing position in 2001. I was delighted with that. So then research-wise, it was a little bit daunting because, so much of my research had been linked to what was available in Tyndall. So my first PhD student, I stayed quite close to what I was doing, except so with printed circuit boards, you can get those manufactured by outside. You don't have to work with Tyndall to get them manufactured. So I went back to looking at printed circuit board magnetics, but instead of using the core materials and the processes in Tyndall, I went back and applied some of the learning that I had got there to see what's the best way of using commercially available cores to achieve functionality in a circuit board. So Christina Collins is one of my first PhD students to do that. And so she and I looked at saying, well, what if instead of having one big inductor, you could split it up into 2 smaller ones or 3 smaller ones? Would you get better performance out of it? And in some applications, it was true that, yes, it's better to have 3 smaller inductors. You get much better efficiency than having one bigger one, because the constraints of the core sizes meant that you couldn't optimize it the way you might want to. And the other thing is that it allowed us as well to have more flexibility in terms of how we would operate the circuit. So that got me more into looking at the magnetics and their applications in the circuits and developing circuits. So we had, of course, some nice publications out of that. I did get back to looking at magnetics on silicon. I was able to convince one of my final year project students, Kieran Feeney, that magnetics on silicon was a very exciting area to work in. So he signed up for a PhD. And at that stage, Tyndall had gone further into developing core materials and very high frequency core materials, and producing different winding shapes as well to optimize or to exploit the properties of those core materials. As well as that, we were looking at, instead of having just one coil under the core, we were coupling windings, so we'd have that winding and this winding connected together under the core and so on. Again, trying to get the power density so that we could convert more power in a smaller space. He was very productive in terms of his publications, and I guess it's that thing of when you collaborate with people, the sum of individual parts, or the sum of our combined contributions was more than the sum of the individual parts. So it was really a nice project to work on. And just very quickly, I did have one other project where we were looking again at the interaction between the circuits and the components, and how you could kind of co-optimize the circuits and the components so that you get the best overall performance. That's another PhD student, Josef, who's actually now working independently in Tyndall himself. So then that's all about power supply on chip. For the rest of, I think I'm pretty good on time. Yes, I'm okay, so good. So the rest of the presentation is going to talk to you about some of the applications I've worked on, so other than power supply on chip. The first one is energy harvesting. So energy harvesting is a bit like renewable energy, but on a much lower power scale. So it's like harvesting energy that's freely available in the environment if you put in some devices to capture it. And why it's important is that you probably know there's sensors everywhere anymore. You probably all have a carbon monoxide sensor at home, maybe temperature sensors in your houses, biomedical applications. People have wearable sensors to monitor their vital or their health, and so on. And there's a whole area called Internet of Things, where you've got sensors, and the sensors are collecting data and they're transmitting it up to the cloud. I'll explain later, Mom, about that one, the cloud. That gets her. And the virus is on the computer and all that. She thinks it's hilarious. But anyway, we'll get there. So anyways, to be able to function and to transmit their data, they need power. So they need a source of power. And a lot of them have batteries. And the batteries, of course, run out, and you have to replace them or you have to recharge them. And batteries are made out of a lot of materials that are not really good for disposal. So energy harvesting is a perfect place to try and supplement the battery energy. So some of the applications we've looked at. So the first one, again, this was one of my first projects when I came back, was with Damien Carroll. And we said we'd look at wearable generators. It was kind of inspired by, we had looked at magnetic micro actuators, like mini motors in Tyndall on silicon. And I said, well, I don't have silicon, but we can try and look at electromagnetic generators using coils and magnets. So you can see here what it is. It's a coil of wire. This time it's like a normal coil of wire, where you'd have lots of turns wound around this structure. And then inside you put magnets, permanent magnets. And the magnets, when the person, if they're in the sole of the shoe, when somebody walks, the magnets will fly back and they fly back when you put your foot up, and they fly forward when you put your foot in that motion. So it's very small amounts of energy, but it's freely available in everybody if you were to put an electromagnetic generator into your shoe. So, or on the side of your shoe. And there was lots of people looking at this at the time. So that's why there was people putting them outside their shoe and putting them under the heel. So you'd actually notice a lot if you had something under your heel and that it was kind of like a motor that you actuated. It was being looked at for things like gait monitoring for biomedical applications or elite sports performance. And I think there are some famous shoes that do have sensors in the shoes. So that's right, Anna. Yeah, thank you. That would need power. So it was a very interesting project and kind of challenging because the level of power is so low. Any power that we got, we needed to harvest it and save it. And yeah, so the power that's being generated all the time is quite low. But by careful design of the coil and the circuits that convert the coil into electricity, into a form like a battery provides, into a DC voltage. So it's not exactly a very flat DC voltage. But you can see that's when you take one step, the magnet goes up and back, so you get 2 pulses of voltage, and that's another step. And in between, the person would have taken a step with their other foot. Okay, so what you're looking at is that's the voltage that the generator is producing, and then this is the voltage on a sensor, a sensor transmitter, to indicate that the voltage that we were providing by the generator through the power electronic circuits was big enough to cause the sensor to be able to transmit its data to a reader. So that was very good. It was a lot of, optimization of the coil and optimization of the power circuits so that they would hold the charge and that there was enough energy then so that's an example. The bottom graph is a different type of circuit, and we were able to, keep it on, the device on for longer with a different circuit. So that was very exciting and nice. We presented a paper at APEC, and that has been quite highly cited. And it was also published in the Institute of Mechanical Engineers. And some of the papers that have cited it, the same kind of structure has been investigated in other applications. So like in wave generators, they would also have this kind of thing where the wave would be moving up and down and so on. We also looked at energy harvesting from indoor solar cells. So these are like normal PV photovoltaic panels that you might see on your roof, except they're much smaller. And these cells were being developed by a startup company, SolarPrint, in Dublin. And we got funding from the Irish Research Council to support Dave Newell to complete a master's originally. So the cells they were developing was the materials that they were using, they're more responsive to the wavelengths of light provided from indoor lighting. So they were being developed specifically for indoor lighting to produce power. Again, we looked at it in relation to a carbon dioxide sensor to see could we operate a carbon dioxide sensor using a solar cell. So where the size of the cell would be comparable to the size of the carbon dioxide sensor. So again, it was, power management and so on. And what you can see here is, it was generating very low levels of power. This time we had to store up the power until there was enough available to operate the sensor. Then the sensor would operate and the voltage would go down a bit, and then it would charge up again. So it operated quite well because you have low amounts of power for a long amount of time, but the sensor operates only for a very short time. So it's a good combination of storing up the energy and then feeding it out in a short amount of time. That work was presented at APEC. We got invited to an industry session at APEC that's sponsored by the Power Supply Manufacturers Association, and that they've got an energy harvesting forum, which is a mix of academics and industry who are trying to push and develop products, I guess, for energy harvesting. Then moving on to radio frequency identification, energy harvesting from that. So I'm sure you've all used an access card either in a hotel or in an office to get into a building or whatever. It works on the principle again of wireless power. There's a coil in here, and then there's another coil in here. The coil in here is being supplied by power all the time, and it's sending out signals. And once a card comes in contact with it, there's a link, a power link to the card, and that sends enough power to the card for the card to be able to transmit the information that's on it, like a code or your name or whatever. And then if it matches with the database that the reader is connected to, it'll provide you with access. So we worked with HID Global, who coincidentally my husband used to work with a long time ago. So I knew some of the people involved in there, the researchers involved in this side of the research. And a normal tag so this would be the reader, and this would be the tag circuit. Don't worry about it. What they wanted is for us to design another antenna circuit. Oh, what have I done? Oh, sorry. To design another antenna. So they have this antenna, which is the normal one doing the RFID, the access. And we designed another antenna inside in that, and circuitry. It's very, very small circuitry because it has to be in a card. The idea was they wanted to have additional functionality in their cards so that they could make them more secure. It's like two-factor authentication, if you like. So we showed that we could produce enough power without interfering with the RFID link to light a blue or a UV LED, and that's it implemented in an actual passport card on the reader, and you can see the blue LED is lit. That was very good, and HID were so delighted with it that they've now decided to do another project with us to try and push it further into commercialization so that we can make products. They can implement it in their products. So then medical devices is another application area. So wireless powering obviously is a big part in medical devices. Again, there's a coil here on the left that will be on the outside, and this will be a coil and circuitry on the inside. And that would be used in something like, we were looking at spinal cord stimulators for pain relief, where there's an implant inside in the body with a battery, and that might run for 2 to 3 days, fine, depending on the person's usage. And then outside you'd have to recharge it because they're quite heavy on power, neurostimulators. So then you have to recharge it with a circuit and a coil that's placed on the outside. And again, you're doing that magic of transferring power across boundaries. So it's not just across air now, it's across tissue, body tissue, so that you can recharge a battery inside in a patient and allow their device to continue to work. The issue with that for medical devices is that medical devices are usually implanted in a metallic case so that the circuitry isn't interfering with the body and vice versa. So that does present challenges for wireless charging, and we came up with some novel coil designs to try and alleviate that. We filed an invention disclosure form. We were hoping to that there might be some commercial interest. Not yet, but it's something I might like to go back to when I get a chance again. We also worked with Aerogen on the development of a power supply for a nebulizer. So due to COVID, probably everybody knows what a nebulizer is, and because we live in Galway, Aerogen is, so just in case, a nebulizer, the clever part of a nebulizer is this plate. It's a vibrating plate with very small holes in it, that when it vibrates, it converts liquid into a very fine mist, and that makes it easier for the drug to be delivered. So Joe Grehan is the principal, he's the senior principal engineer in Aerogen, in electronics and software. He was interested in doing a research master's, and what he wanted to do was to try and get a better understanding of each bit of the components in the power supply circuit. I'm not going to go through it. Just to illustrate, there's lots of bits and pieces in it, as well as the fact that the nebulizer load is quite a complicated load electrically to get it to vibrate. So they had a circuit from years ago and that they were using all the time, but because they're developing new products, he wanted to know, well, what were the important parts of the circuit and how did it all really work? And if he made a change in something small here, how was it going to affect all the different bits? So he did a master's in that. He focused first on their existing design, and he found at least two things that made improvements in terms of he was able to reduce the component count, and he was able to make the circuit more immune to variations, manufacturing variations in the vibrating mesh. So that was a nice project. I learned a lot myself from that in terms of the important things in designing medical devices that are to be put into products. I've only maybe 2 or 3 more things to go. I'll go through them quickly. This is the emerging cancer treatment, which is, really, again, amazing products. It's products being developed by Murray Medical in Oranmore. So electroporation involves putting high voltage pulses to the cells, and either the cells, the membrane of the cell is opened so that the drugs go in better, or if you apply high enough voltages for long enough, you can actually kill the cancerous cells. So Jayashri is here somewhere. So she's working on the design of a new power supply to be put into their product, which is delivering the high voltage pulses. And we also have a PhD student who's working on an alternative approach, so it's good to have the two approaches. We also have Hamza, who's here. He's another postdoc who's working on the electrode design to be connected into the generator. So this probe, it sucks in, there's a vacuum that sucks in the tissue to be treated, and then there's plates here where the electric voltages are applied to generate electric fields to cause the treatment. So he's modeling the electric fields, and he's also modeling the temperature to make sure that the tissue doesn't get too hot and it's uncomfortable for the patients. In the interest of time, I'm going to skip out these last ones. It's more looking at system level modeling of electrical components and power electronics. I might mention this one very quickly. This is Mustafa, who is our latest, Rory and I co-supervised with Enda Barrett. He graduated on Tuesday or Monday, I think. But he was working on an NWE Interreg project, which was really cool because we got to see all the latest and greatest in energy storage. So there's a flywheel. I got very excited when I saw that. And then they told me, well, actually, that's just a Photoshop. They put their but their intention is to put a flywheel as storage for excess wind that then could be available for trains if the electricity as a buffer. This one is interesting because it's not obvious, but these are bifacial solar panels. So there's solar panels here and on the other side. It's like a fence. And the idea is to produce electricity in the morning when you need to milk and in the evening when you need to milk, because the sun will go on either side. So that was also, very interesting. But Mustafa's work was to manage, optimize the management of the energy and where it should go at different times of the day and so on. So I'm just going to talk, Leisha, oh no, you didn't talk about our involvement in the GEEK. So the GEEK, for those of you who don't know, and Rory might talk about it as well. So I teach electrical power machines, I teach control systems, power electronics, and all of those topics are implemented by our student team that builds our go-away energy efficient car. So I work with Rory and Nathan and Martin here I work on the electrical components, Rory and Nathan work on the mechanical components, and Martin works on the data side of things and sensors. I shouldn't say we all work on it, we just watch the students work on it. We direct the students to work on this, and it's really exciting because we get to apply our knowledge in the different areas, but they actually teach us more by the end of the year. So yeah, I don't know, you've probably seen it on different occasions. Leisha has already mentioned about the Athena Swan Award. It was during COVID when we did the majority of the work, and it was, I don't know, people were really great for turning up to meetings, which was, maybe it was facilitated by COVID and online, but I actually did enjoy that. I was warned that it was going to be an awful job, but actually it was quite enjoyable working with the team. Just quick acknowledgements. I want to say thank you to Ger. He's been a mentor, a collaborator, and a great, I'm going to get lost for words now, but he has always put me on the right path, I'd say, in terms of advising on what to get involved in, and helping if I ever had any issues and so on. So thank you, Ger. Thank you to the heads of school since I've been here. There might have been one more, I can't remember. But anyway, these are the ones I know for sure who were very... So, that's not fair. I shouldn't have left some... I don't think I left anyone out. Anyway, no, since we became a school, these are the heads of school. And they have all been very supportive to me, providing me with opportunities. That's what I wanted to say about Ger too. He has also provided me with lots of opportunities related to the IEEE, which I'm very grateful for. And the heads of school have provided me lots of opportunity to develop, give me the responsibility for EDI and so on. And also our heads of discipline, Martin is here, Garage, and Professor Dave Wilcox, who was here when I first came. And again, I got lots of advice, and they're always there, support, which has been great. That's my graduates and where they are. I was interested to see. I had a bit of trouble finding photos for one or two, but my sleuth of a daughter was able to find them on social media one way or another. But anyways, it's great to see that, a lot of them are in industry, some of them in academia. And anyways, it's a great picture. And I had never done it before, so it was nice to do that. I've had several collaborators internally, either on projects, co-supervision of PhDs, writing papers. Outside, I've probably mentioned the Tyndall guys, DTU, and so on. Again, writing papers or proposals. And that's some of my industry collaborators that I could remember. So I'm going to leave it there. I know I've run over slightly. So thank you. And I don't know if there's questions, but we can not do them. I'm happy with that.
I think, given that